Okay, so this is a review of Moles and Stoichiometry, and you need to watch this so that you're prepared for the review lesson that we're going to do in class tomorrow. So we're going to review some things that we've already talked about in other units, but still are important when dealing with the concepts that we are in this unit. For example, you all should know that a compound is a substance composed of two or more different elements chemically combined in a fixed proportion. For example, H2O. If I don't have two H's and an O, then I don't have water. And everything always combines in whole number ratios. If it's a compound, then it can only be broken down by chemical means because it was put together by chemical means. So which of these represents a chemical compound? You're looking for two or more different elements combined. So we know it's not 1 and 2 because those are just elements. 3 might look like a compound because it's two different elements, but you can see by the plus sign there that it is a ion. So if you look here, that tells us it's an ion. So the only correct choice would be choice 4, because all compounds are electrically neutral. Now, a chemical formula tells us both qualitative information and quantitative information. The qualitative information is the describing factor. It tells us what types of elements are present. Is it oxygen, hydrogen, nitrogen? The quantitative factor is how many of each atom are present. So over here, if we're looking at H2SO4, the H, the S, and the O is the qualitative information, and the number of atoms is the quantitative information. And you know that we never write 1 for a subscript, it's just implied. Please remember the difference between binary compounds and ternary compounds. Binary compounds are just two elements, two different elements, and ternary compounds have 3 or more elements, and that means that you've got a polyatomic present, so you'd have to use table E if you were doing anything with any of those. Which substance can be decomposed by a chemical change? Again, we're looking for a compound. 3 and 4 are out, they are elements. The Regents loves to put choices 1 and 2 together because 1 is a compound and 1 is an element. Capital C, little o is the element cobalt, whereas capital C, capital O is carbon monoxide. We've learned about 3 different types of formulas this year: molecular, empirical, and structural. Last unit in bonding, we were doing a lot of structural formulas. We were drawing what the compound looked like. In this unit, we've dealt with molecular formulas and empirical formulas. Remember that empirical means most reduced, and molecular means multiple. The molecular formula is a multiple of the empirical. So in this example, CH3 is the empirical. If I times that whole thing by 2, I get C2H6. So the molecular formula would be C2H6. As I said, the empirical formula is the most reduced, and it may be different from the molecular formula, or it may be the same. For example, in water, H2O, that cannot be reduced. So the empirical formula is H2O, and the molecular formula is also H2O. In both of these examples here, it can be reduced. The molecular formula, hydrogen peroxide, can be reduced to HO. 2 goes into 2 once, and 2 goes into 2 once. Glucose, C6H12O6, 6 goes into 6 once, 6 goes into 12 twice, and 6 goes into 6 once. So the empirical is CH2O. So which is an empirical formula? Well, you're looking for the one that cannot be reduced, which would be choice 1. Here's some examples of empirical formulas and their molecular formulas, and you can see the multiple. Now, if the empirical formula and the molecular formula are related by a multiple, then so is their mass. So for example, hydrogen peroxide has a mass of 34. Its empirical formula is half of that. It's HO, which means that HO has a mass of 17. And you can look at the other examples and see the same type of relationship. Remember, when we're writing formulas, and I'm not saying that there is a formula on there, but there may be, you have to drop and cross. You look up the oxidation states of the metal and the non-metal, or a polyatomic, and then you drop and cross. So for this example that we're doing here, we're looking at carbon and oxygen to write a formula for carbon dioxide. C is +4, O is -2. We drop the signs, then we cross, and we get C2O4, which then can be reduced to CO2. Same thing with a polyatomic. However, when you drop and cross on polyatomics, if the subscript is greater than 1, you need to put the polyatomic in parentheses. So here, ammonium has a +1 charge, phosphate has a -3. When we drop and cross, we get NH4, 3 PO4. We don't need to leave the PO4 in parentheses because there's only one of them. Remember, the oxidation states are in the upper right-hand side of the element box. Polyatomic ions are found in Table E. And let's quickly review naming. Between a metal and a nonmetal, you're going to name the metal and change the ending of the nonmetal to IDE. So, for example, here we have aluminum chloride, which is AlCl3. This was +3, this was -1. We dropped and crossed. Oh, it's ammonium chloride. Sorry. Well, we'll do ammonium chloride here. So we've got NH4 to polyatomic with a +1 charge, and Cl with a +1 charge. Aluminum oxide, Al is +3, oxygen is -2, so when we drop and cross we get Al2O3. Barium is Ba +2, sulfide comes from sulfur, so it's just BAS because this is 1:1. Zinc fluoride, Zn is +2, and F is -1, so the formula would be ZnF2. If you have a polyatomic, it gets easier because you don't have to change any endings to "ide." You just name the metal and name the polyatomic. If it's two polyatomics, just name both polyatomics. Remember, if you have an element that has more than one positive oxidation state, these are typically found in groups 3 through 12, but there are some exceptions outside of those groups, and that would be tin, antimony, and lead. These are found outside group 12. They're to the right, they're like groups 13 and 14, but they have multiple positive oxidation states, so we need to use a Roman numeral. This Roman numeral came from the copper, so what it's telling us is that copper is +2. So copper is +2, SO4 is -2, so they combine at a 1:1 ratio. If I said iron, Roman numeral 2, oxide, then that means that the Fe has a +2 charge, and oxygen is -2, so the formula is simply FeO. Remember that all compounds must have a net charge of 0, and if it's an ion, then the charges equal the charge on the ion. For example, MgCl2. This is -1. -1 times 2 is -2. So Mg had to be +2, which we know it is because it only has one oxidation state. If I'm doing NO3 -1, oxygen is -2, that gives me a net -6. But here the charge doesn't equal 0 like it did here, it has to equal -1, which means that nitrogen had to be +5. And this is just showing you PbO2 down here. I can do this one out quickly. PbO2, oxygen is -2. That gives me a net -4. This whole thing has to equal 0, so Pb had to be +4. Because this is a element with more than one positive oxidation state, we would have to name it lead Roman numeral 4 oxide so that we would know which oxidation state was used. Which formula correctly represents the composition of iron 3 oxide? I do not know why there's a hyphen there. Iron 3 oxide, that means we're using the +3 on the iron, and oxygen is -2. So when we drop and cross, we get Fe2O3, which is choice 4. Choice 2. Remember nonmetals. You need to use prefixes, mono, di, tri, tetra, except for if the first element is 1. As an example here, carbon dioxide. The carbon is 1. We don't say monocarbon on the first element, we just name it. And then there's 2 oxygens, so we're going to use the prefix dioxide. Here we have 1 and 1, carbon monoxide, and so on and so forth. Remember, in all chemical reactions there has to be a conservation of mass, charge, and energy. What we start with, we must finish with. This is called the law of conservation of mass, the law of conservation of energy, and the law of conservation of charge. A balanced chemical equation represents a conservation of atoms, and the coefficients in a balanced chemical equation can be used to determine the molar ratios. So here I have a word equation and my chemical equation, and it says 2H2 plus O2 yields 2H2O. So I have 4 H's on the left, 1, 2, 3, 4, there they are. 4 H's on the right, 1, 2, 3, 4. 2 O's on the left and 2 O's on the right. So if I had, if I had 10 grams of hydrogen and 15 grams of oxygen, then this would have to equal 25 grams. This is what we mean by what we start with, we must finish with. It may be rearranged in different forms. If an equation is balanced properly, both sides of the equation must have the same number of, hopefully you said, atoms, because when we balance an equation, what are we doing? We're saying that we have 4 H's, we have 2 O's, and on this side we have 4 H's and 2 O's. We are counting the number of atoms. Balancing the equation, some of you have gotten really good at this, some of you still need some practice. You've got to figure out how many are on the left, how many are on the right, and what do I do to get them balanced. When I look at this, I can see right away that I have an uneven number between oxygens. Therefore, because this number is odd, I'm going to be looking for the least common multiple. So I can put a 3 here, make that 6, put a 2 here, make that 6, 2 times 3 is 6, and then I've got 4 irons, which is what we wound up doing down here. So, in this example, we've got a polyatomic. And what did I tell you about polyatomics? If polyatomics are present and they stay intact, deal with them first. So I have 1 SO4 unit on the left and I have 3 SO4 units on the right. So I have to put a 3 here. That's going to give me 3 CUs. So I have to put a 3 here. And I have 1 AL here and 2 here, so I'm going to put a 2 here. So the coefficient in front of the AL is the 2. in this example, I've got 3 oxygens here, 1 oxygen here. It's a total of 4, and I have 2 here. But if I put a 2 here, that'll even up my oxygens, right? Nope, I'll have 5. That's not going to work, is it? If I put a 3 here, then I'll have 6, and now I have an even number. So 3 oxygens here, 3 oxygens here, 6 oxygens. How do I get 6 oxygens? I put a 3 here. 3 times 2 is 6. Now I have 3 carbons. Well, and I have 3 carbons there, so that worked out. I have 2 Fe's here, 1 here, so I'll put a 2 here. So in coefficient in front of the CO, carbon monoxide, is 3. Regents loves pictures of the mind. So instead of giving you actual compounds and elements to work with, they give you pictures. And this is usually to demonstrate a law of conservation of mass problem. Here they're telling you that if you have 2 different diatomic elements, they split up and then unite. So if you are given box A, what will result in box B? You know that a black and a white pair up. So one of these is going to go with this and one with this. So you've got, this is a bad color. So I've got this. That's what I'm doing, okay? I'm going to do that till they're all paired up. And what I wind up getting, as you can see, is I have 4 of these, and then I have the 1 pair left over. This will be unused, and you still have to draw it. Use the coefficients to predict the amount of a reactant consumed or a product formed. These are called mole-mole relations. And most of the time when we're doing mole-mole relations, we're using a balanced equation and we're setting up a proportion. The best thing you can do is, as you read the problem, write what you are given in the balanced equation. How many moles of oxygen? Well, I don't know that, so I'm going to put an X here. Are produced when 4 moles of ClO3 react. So now I've got my proportion set up. 4 over 2 equals X over 3. And then I cross multiply and divide, and I get 2x equals 12. Therefore, x equals 6 moles of O2. Here's another one. How many moles of oxygen, I'm putting an X, are required to react completely with 1 mole of C2H2? And C2H2 is ethyne, so we've got 1 here. So my proportion is going to be 1 over 2 equals x over 5. Therefore, 2x equals 5, and x equals 2.5. In another problem, what is the total number of moles of water? I put an x here, needed to make 2.5 moles of glucose. So I've got x over 6 equals 2.5 over 1. So I have x equals 6 times 2.5, which is going to be 15. Given the reaction, what's the total number of moles of NaCl? So my x goes over the NaCl when 2 moles of sodium chromate are used. So my proportion is 2 over 1 equals x over 2. And I've got x equals 4. The formula mass of a substance is the sum of the atomic masses of its atoms. The molar mass, or gram formula mass, is the substance that's equivalent to 1 mole. The only difference between formula mass and gram formula mass are the units. So here, the formula mass is 98 AMU, but the gram formula mass would be 98 grams per mole, which is what we're showing here on this page. So once again, the only difference between formula mass and gram formula mass are the units. A compound has a gram formula mass of 56 grams per mole. What is the molecular formula? Well, this you're working backwards. You basically have to figure out which one of these adds up to 56. And this is the empirical. So what I would do, you can just find the GFM of all these, but I can see here that 12, 13, 14. I can see that the empirical formula, CH2, is 14. 56 divided by 14 is 4. So 4 times CH2 is going to give me C4H8. I can double check that. I've basically got 4 times 12, which is 48, and I've got 8 times 1, which is 8, which is going to give me 56. And I just rounded the math on the mass on those because I was just trying to get to the formula quicker. The gram formula mass of NH4Cl is, well, we've got 1N at 14.0067. I've got 4 H's times 1.0079, and I have a Cl at 35.453. So very quickly, since this is a multiple choice problem, I'd probably do 14, and I do 4, and I do 35. So I'm going to get 8 and 5 is 13. I'm going to get 53. So choice 3. Now, the other thing that you can do with moles is if you're given problems, you can use the mole formula or calculation in table T. So you have to look at what you're given. If you're given a balanced equation, you're going to do the mole-mole thing, set up a proportion. But if you're just given a word problem and you're given grams and they want you to find moles, or they give you moles and they want you to find grams, you're probably using the formula moles equals given mass divided by GFM. So here, how many moles in 49 grams of H2SO4? So you know X moles equals the given mass divided by the GFM. You get your answer. Dimensional analysis, I just write 49 grams, and I know grams has to cancel, so it goes in the bottom. So 1 mole equals 98 grams. And now I just cross out my grams and I divide, and I get the same answer. How many grams are contained in 2 moles of H2SO4? So now they gave you the moles, you know the GFM, and they want you to find the given mass. So when they ask you to find grams, they're referring to the given mass in the formula. You'd have to put a 1 here, and you've got X equals 2 times 98. Dimensional analysis, I just do 2 moles, and I know that I want moles to cancel, so that goes in the bottom, and 98 grams goes here, and I just multiply and I get the same answer. Percent comp. Remember that percent comp is equal to part over whole times 100. It's in your reference table. Please make sure you hit the equal sign once you divide and then multiply by 100, or it can mess with your order of operations in your calculator. It's always best to circle what you're looking for. Here they want the percent of oxygen. So here's my oxygen in the whole thing. And then you've got your part is your 64 over your whole 98 times 100. What is the percent mass of oxygen? We just did this. So this is my part, this is my whole. 4 times 16 is 64 over 98 times 100. Sorry, that was the same example. 65. Alright, percent mass of hydrogen. This is my part, this is my whole. So I've got H 3 times 1.0079 which is approximately 3. I'm doing multiple choice, so I'm not going to have exact numbers. N, I've got 1, 14.0067. So this is my part, and my whole is this plus this, which is going to be 17. So it should be choice 4. The percent by mass of calcium in the compound calcium sulfate. Well, Ca should be 40, S is about 32, and oxygen is 4 times 16, which is 64. So my whole is going to be 136 is my whole, and my part is 40. So I've got 40 over 136 times 100. And that's going to give me 29%. Remember, a hydrate is a compound which has water trapped in its crystal structure, and we can determine the percentage of water in a hydrate. So here, they're telling you this formula is got copper sulfate pentahydrate. For every 1 copper sulfate, there are 5 water molecules trapped. So if we wanted to find the percent of water in this hydrate, we're going to do the same thing. This is going to be our part, and this is going to be our whole. So 1 water molecule, oxygen is 16 plus 2 hydrogens, is about 18. Now they separate it out. I tend to do it differently. I just do H2O, and I've got 5, so I've got 5 times 18. And I'm going to get the same thing. 5 times 8 is 40, so this is going to equal 90, which is what they got here. So my part is my 90, and the whole is the whole thing, so 36%. What is the total number of oxygen atoms in the formula? So they just want to know the number of oxygen atoms. So you've got 7 times 1 is going to be 7. Ooh, I'm sorry, my mistake. There's 7 in the water. They want to know in the whole formula. So water is 7, and we've got 4 in the MgSO4, so it was 11. Read too quickly. Let's talk about types of chemical reactions. You need to know these, and I'm going to give you flashcards tomorrow. Synthesis, decomposition, single replacement, double replacement. Synthesis is like marriage. 2 things come together, 1 product. Decomposition is the opposite of synthesis. It's like divorce. You have 1 reactant, and it splits into several products. Single replacement, remember, that's like, you've got a girlfriend or a boyfriend, and a new hottie moves into town. We don't lower our standards, we raise our standards. So you take on the new hottie, and the old boyfriend or girlfriend gets kicked to the curb. So this is the couple, and this is the hottie, basically. And we'll see how that works. So hottie pushes the old hottie out, gets kicked to the curb, and a new couple forms. Double replacement, 2 compounds, kind of like swingers, and they switch partners. So here's our synthesis. Notice, 1 product. That's a good way how to recognize synthesis. 1 product, forming a union. Here's an example, and these are the examples I gave you on the flashcards that I'm handing out tomorrow. Decomposition, notice, 1 reactant splits in to 2 things. Single replacement, remember, this is always plus minus, plus minus. So here you have C replacing B, and B gets kicked to the curb. We have to use table J for this because we need to make sure that the element that is pushing in is above the element that it's pushing out. Sorry. So if you look at table J, zinc is above copper, it can push it out. Double replacement, this is plus minus, plus minus, plus minus, plus minus. So plus hooked up with minus, AD, and plus This is written backwards. This is written backwards. It should be CB. C is the plus and it hooks up with the minus. We always write the plus first, then the minus. And then it says check for table J, F for insoluble compounds. We haven't talked about that. We're going to talk about it in the next unit. And lastly, combustion. You have some molecule X that combines with oxygen to produce carbon dioxide and water. These will be the same, okay? Always the same in any combustion reaction. This one will change. So here's an example using decine and oxygen to produce carbon dioxide and water. This is table F. We're not going to worry about this right now. We're going to talk about this in the next unit. Here's an example of a single replacement reaction where the more active metal replaces the less reactive metal. Again, we go to table J. J is above PB. Therefore, PB gets kicked to the curb and Zn takes its place. And remember, when the new compound forms, Zn with Cl, you don't just bring this Cl2 over here. This is a +2 charge, a -1. We have to drop and cross. Now, if Pb, we're trying to push in on ZnCl2, there's no reaction because Pb is lower than Zn in table J. Here you can see that Zn pushes Cu out. Here is Zn, and it's above Cu. But Cu cannot replace Zn. Hydrogen is also on table J, which shows you that metals will react with acids to produce hydrogen. So here, Zn pushes H out to produce hydrogen gas because it is above hydrogen on the table. So according to reference table J, which one of these metals reacts most readily with HCl to produce H2? Now this question can be a little tricky. And the reason it can be tricky is because maybe more than one of those will react with the acid. The key there is most readily. So you want the one that is most reactive. Therefore, you're going to want the one that is highest on table J. So you should be looking at table J. I set mine to the side for a second. And in table J, we see, I believe, that potassium is highest. So when we look at these and we rank them according to table J, you've got potassium on the top, followed by Ca. Underneath that you have Mg, and then Zn. So because this is the highest, it's the most reactive, so that's our answer. All of those would react with the acid in a single replacement reaction, but they're asking for one. Which one reacts the best? Double replacement. The reactants are in solution, and one of the products is usually not soluble in water. That means a precipitate forms. That's kind of looks like curdled milk, and that's what table F is for, but we're going to look at table F a little bit later. So remember, the first one's always positive, negative, positive, negative. So A hooks up with D, and C hooks up with B. Okay, and lastly, just a review of the calculations you must know for this unit. And this is what the quiz will be on tomorrow. Calculating gram formula mass goes without saying. So if I give you H2O and I say what's the gram formula mass, you have to be able to go H2 times 1.0079. Oxygen, you've got 1 at 15.9994, right? So then you come out with 18.015. I don't even know. 8? I'm not even sure. Let me just quick add them up. I don't know off the top of my head. It's going to be 52. 0.0152. Okay. So you need to know how to do that. You need to know how to calculate percent composition. There'll be one of those there tomorrow. Mole calculations using the formula, meaning moles equals given mass over GFM, and then using the balanced equation and setting up a proportion. So that's when you have, you figure out x over 2 equals 3 over 4, and then you solve for x using the balanced equation. Empirical formula, percent to mass, mass to moles, divide by small times till whole. Remember, if you're given percent, you're just changing the units. So 25% is equivalent to 25 grams. All right, and then you're going to find moles, divide by the smaller number of moles times till whole. Review that in your notes. And then molecular formula, there's 3 steps. First, you have to find the empirical formula if you're not given it. Then you need to find the empirical mass. I wrote this backwards. Sorry. It is the bigger one, molecular mass, always larger, divided by the empirical mass, and that equals your multiple. Sorry about that mistake. Once you find this multiple, this is going to be a whole number, you take your empirical formula, multiply it by that multiple, and you get your molecular formula. Okay, that's it.